Okay, hello everyone. Welcome to our CIAN lecture today. My name is Dan Kilper. I'm a professor here at the University of Arizona, and I just want to say a few words of introduction. First off, CIAN is the Center for Integrated Access Networks. We're an engineering research center funded by the NSF, and the NSF is funding is going toward supporting this activity as well as the other activities of the center. And we're also supported by our industry affiliates. Their membership go towards making events like this possible, and we'd like to thank them for their support. I want to mention that well, this will be a regular lecture series, and in January we won't be having a talk, though, because we have our industry affiliates meeting, and we will be having a workshop at our industry affiliates meeting that will take place in San Francisco on Monday, February 3rd, and that's going to be on photonics communications. It'll be a half-day workshop in the afternoon. So that'll take the place of our next CIAN lecture. And then in February, we will have a lecture again that will be at UCSD. So you'll be hearing news about that. And today's presentation, it's great to see the audience here in Arizona. We also are broadcasting this over the web, and we have a crowd online on the webinar. And in fact, these lectures are going to bounce between different locations. So the next one, as we move to UCSD, folks here will be able to tune in over the web and join online as well. For those of you who are online, let me just confirm, folks, are we coming through online? Any response out there? I don't know. Sorry? Yeah, we're not muted here. So if someone online, if you can respond on the chat line for the go-to meeting and let us know that you're hearing everything okay. So what will happen is at the end of the presentation, we'll unmute the microphones for everyone, and you can also use the chat feature for a go-to meeting to type in your questions or raise your hand if you would like to do an audio question. Okay, are we getting anything on the chat, Yusuf? Okay, if anyone online there can let us know that we're coming through okay. Let's see, these are always one of the problems of doing these things online is getting the online part working. Hello, I'm hearing some audio on the phone here.
It's a fax machine. Beep.
Okay, maybe Yusuf, can we mute those lines?
Now that we've heard them, we don't want to hear them.
Okay. Okay, I think we have the audio going through. So let me go on to say, in addition to our industrial affiliates meeting in San Francisco, we also have our a workshop at OFC, the Optical Fiber Communications Conference, that we put on together jointly with the OIDA. And in this workshop, the theme will be software-defined photonic and data center networks. That's going to take place on March 9th, running all day that Sunday before OFC. So we look forward to that event and hope that folks can make it for that event. Okay, with that, that's all I'm going to say. I want to hand it over to Bob Norwood, who's going to introduce our speaker today.
So thanks, Dan. So just a few quick words about our speaker. So Pierre, Dr. Pierre Blanche, is assistant research professor here at the University of Arizona Optical Sciences Center, College of Optical Sciences. And Pierre, I guess I'm trying to remember exactly when he joined us again. I wasn't here the first time he was here, and then I came, and then he came, and we've worked together on this area holographic 3D display and holographic optical switch, and Pierre was really a key and critical member of the team that demonstrated holographic 3D display, and in particular holographic telepresence, which was a Nature paper a few years back, and really pointed the way toward drowning the internet. And so then we had to think about, because if everybody was really doing holographic 3D display all the time, the internet would drown, for sure, as you'll see. And then he started worrying about that, so then he thought, okay, maybe we should work on some way to fix that. So that's the holographic optical switch, still based on holography, because he really knows more about holography probably than anybody, on the planet, I would guess. And the other thing I would say personally about Pierre is that he keeps the most fantastic notes of anybody I've ever met. So if you want to learn how to keep track of what you're doing, Pierre is the gold standard. So without further ado, I will introduce Pierre.
Well, thank you, Bob, for the kind introduction. And I think I don't need that microphone, so let. I will need it because I have the other one. I'm good. Yeah, well, thank you for the invitation, and this is my great pleasure to initiate this cycle of CIAN lecture series. And today I would like to share with you the big picture about our research on holography. And for that, I need to start a long time ago, because I vividly remember the very first time I saw a hologram. And it was at the Palais de la Découverte in Paris, France, a museum dedicated to science and technology. And I should have looked a little bit like this, because I was really mesmerized. How a seemingly transparent piece of glass could project a three-dimensional image. While my classmates roamed all parts of the museum, I stayed there for hours trying to figure out how it works. I was baffling. And of course, I could not figure out, at least not that day, but I was hooked to this day. And this is only much later that I should learn it works because of this. This is the Kirchhoff diffraction integral. And well, I pretty much had the same expression on my face both days, because at first I was as much puzzled by the math that I was with the real object. But no, I can say, I think I get it, and maybe I can retire. But no, I cannot retire. And I'm going to tell you why. It's because if we can produce an hologram pretty much any way we want, we still not have an holographic television. The question is, do we really need one? Because the name of the game here is not necessarily to have an holographic television per se. It can be any type of display, any type of technology, providing it reproduces all the visual cues. So we want a screen that reproduces reality. Yes, Trin? Fantastic. So we want to have a screen that reproduces reality, I was saying. Well, at least reality visually. I'm not speaking about teleportation here. Don't get me wrong. And then when I say we, it's not just me and a bunch of or handful of crazy scientists. It is we, the people, who want to display a more perfect image. So humans are meant to see in 3D with parallax, occlusion, accommodation. Not only a 3D display is fancier, but it also allows a better, more precise, more effective interpretation of the information. And this has been proven. Look at that chart. Well, it is fantastic, really, clearly. But maybe a little bit of explanation will convince you. Because what happened here is that teams of soldiers were given their usual 2D maps and picture, and they were asked to do their usual tasks, like, search and destroy, avoid enemy fire, and blow stuff up. And then they were given holographic 3D map, such as these. They exist, really. You see, with such a map, you can see around building. You can see terrain elevation, humps and valley, and you can immediately interpret vegetation density. So with these 3D maps in hand, the same teams of soldiers were asked to perform the same task. Well, they changed the target because they were blown the first time. So at the end, the authors analyzed how well they performed, and they did significantly better in each and every single task with the holographic map. See, the red bar is their score with the holographic map, and the blue bar is their score with the 2D maps they were trained with in the first place. So they were used to those 2D maps. And I mean, this is something. This is not 3 or 4 tasks. This is all of them. And when they ask which one they prefer, all the team choose the hologram. And of course, because even if they are soldiers, they are above all humans. And they have 2 eyes, and they have lateral to see lateral disparity, and they have ciliary muscle to accommodate, and lateral muscle to direct the image to their fovea. So now imagine what your surgeon can do with such a map. Not that I want to send him to the battlefield, but if I want him to devise the best strategy for an operation, should we provide him with this 2D slide of the body where he needs to mentally reconstruct the volume, or that, a direct 3D representation where he can immediately apprehend all the aspects of the organ and manipulate the projection with hand gesture in real time? So think about what this kind of improvement seen for teams of soldiers mean for a surgeon in terms of life saved. So 3D displays are not just gimmick and gizmos. They can be really useful for a variety of application and profession where visualization is critical. It can impact everyone's life because a successful technology will replace every single 2D display. And by the way, this particular image is part of a commercial for an actual display that looks like this. And I want to play a video. Should just click on it. Sorry for the people online, I think the video won't play. But you can see 3D, lateral disparity. You can manipulate it with the stylet. But there's no hologram there. No other hologram whatsoever. It's just a parabolic mirror, but it works. So I'm going to close it and go back to the presentation. And that's not the first time that there exists a plethora out there of so-called holographic display that reproduce 3D, but are not holographic at all. And some are not even 3D, like the motion display that you have certainly seen. And here is Tupac, unseen after he's dead. So it's not really there. And I like also this one. This is Madonna. Not that she's dead, but the gorillas character next to her do not exist. But you just can tell because it's a cartoon, but it looks alive and real. So they are just, in this case, they are just projected on a semi-transparent screen, and your brain is full. It looks really alive. So what is missing here? Do we really need holographic 3D display when this looks so good? And to answer this question, we are going to take a journey into various 3D display technology. So here they are. Well, most of them on this chart. And in the taxonomy, there is a first split right at the top between orthostereoscopic and stereoscopic display. So we're going to start with the stereo pair system when we explore this chart. And you certainly know that stereoscopic display project 2 images, and 2 images only, 1 for each eye. The trick is you just have to put a barrier to prevent the other eye to look at the wrong image. And this technology is very old. It's older, actually, than photography itself. The first display used hand-drew pictures. You might also recall the ViewMaster when we were children. I don't know if they produce it still, but I used to have one of those, and that's great. Today, in 3D theater and the 3D television use the same principle, and the audience use the glasses. And that's the problem, the eyewear. Because if the public is ready to accept it in theater, and personally I love it. Each time I go to theater with my children, we pay the extra few bucks for the 3D because it's so much more impressive. But for the living room, wearing those goggles all the time, well, not really. And I'm not the only one who thinks so, because if you look at the sale of the 3D television, they are not skyrocketing. And I would like to know in the audience here, who has a 3D television in their living room? So don't be shy, raise your hand. We're not going to laugh at you. Yes, we did, sorry. So just one on maybe 50 people. So that makes my point. Well, they're great, but, oh, you have one in your lab. That doesn't count. It's a lab. So this technology is not really rocketing, and for good reason. And I'm going to tell you why. Because even with the eyewear, stereoscopy do not reproduce all the 3D visual cues. There is no motion parallax, and there is no accommodation. And this matters. This actually matters a lot. So I need to tell you a few words about the disparity between accommodation and divergence. So you see here, when you look at a real object, your eye pivots into the socket. This is divergence. But also your ciliary muscle pull and stretch the lens in your eye to accommodate the image in your retina. However, into a stereoscopic display, when your eyes indeed converge toward an object in front or in the back of the screen, the focal distance is the screen itself, always, and not the supposedly 3D object. So there's a conflicting information between the accommodation in one hand and divergence. And your brain cannot figure out exactly where the object is. So you might not notice it. If you go to theater, you might not notice it. But your brain certainly perceives it. And it can lead to all sorts of bad feelings, like headache, eye strain, nausea. So such a system is not very well suited for children whose visual system is still under development. It's not even well suited for you for several hours a day, every single day. So stereoscopic systems are not good enough. We need to find a better technology. So after eliminating the stereoscopic system, what's left? Well, all the other autostereoscopic techniques. So those techniques, autostereoscopic, do not require eyewear. They are projecting images that change with the angle. So your left eye and your right eye see different images without the eyewear. And I already also eliminate some that suffer the same problem as stereoscopy, so the accommodation and divergence disparity. So let's now have a deeper look at the volumetric 3D display, because there is certainly quite a lot of different systems out there. But what they have in common is that the different views are projected inside a volume or from a volume. And since your eye are directly looking inside that space, well, there is no conflict. Accommodation and divergence are correctly reproduced. The way the projection happens inside that volume can be different for different systems. And I show here a rotating mirror from UCSD, or plasma bubble generated by focusing a laser in the air or in a liquid that has been done in Japan, or diode filling the space, lots and lots of diode. So the problems of those displays are specific for each technique, and you might have shaft artifact, for example, in the case of the spinning mirror, or difficulty to reproduce color in the case of the plasma bubble. But every time you cannot correctly render the occlusions, which is really unfortunate. So this means you cannot mask the background with the foreground. You can only do that for one very specific position of the viewer. Once your viewer moves, or if you have different people in the room looking at the display, occlusions are not well respected. And that ruins the whole 3D experience. So unfortunately, volumetric 3D displays that are quite simple cannot reproduce all visual cue either. So let's turn our attention to yet another technology. And here's my favorite one, holography. I will try not to get biased, but it's going to be very difficult for me. So keep me on track. So in holography, you have to calculate or optically produce a diffraction pattern. The diffraction pattern is the hologram. From that diffraction pattern, a reading beam gets scattered, and it reproduces the light field as it was initially emitted by the real object. Do you remember the Kirchhoff diffraction integral? This is how we calculate the diffraction, or this is how nature produces it. And when I look at it, I'm still amazed today. So when looking at an hologram, you see the same thing, the same light field as if the object was present. This means you see it in 3D with all the visual cues, no exception. And this is the reason why holograms are far superior to any other technique. Well, you tell me if I'm biased here. The hologram can get so precise that you can even perform very nice experiments like interferometry and measure the form to an object to sub-wavelength scale, or analyze the vibration mode like on this picture. You see those rings where the guitar is vibrating. But there's a glitch. And I have to admit it, even though I do not like to admit it. You see that diffraction structure, it can take different forms. But to be efficient, the pixels need to have about the same size as the light wavelength. So for the visible, it's about 500 nanometer across. 5 nanometer per pixel. For a reasonable size screen, which is half a meter by half a meter, you do the math, multiplication, that means 10 to the 12 pixel. It's no big deal. I can generate that if I use a Cray computer within a week. But if I want a video display at 60 Hertz with 3 colors and 16 bits per color, multiplication gives 10 to the 16 bits per second. We enter the domain of peta bits per second. And I'm not talking about people eating tasty animal here. Okay? I'm talking about extremely large volume of data. So let's pause for a moment and look at what that number 10 to the 16 bits per second really means. And that's a fun test to do. I plot the speed of different telecommunication systems according to the time of their introduction. And I start with the sharp semaphore, you can see it on the background, introduced in Napoleon's time, the end of the 18th century. It could send an average of 2 words per minute. That is, as you certainly know, about 6 bits per second. The electrical telegraph, now patented by Benjamin Franklin in 1750, but only introduced a century later, certainly improves upon the mechanical semaphore. Because using the Morse code, it can send an average of 30 words per minute, or about 100 bits per second. Now, the telephone, at its introduction, was just a sophisticated telegraph and can have claimed to transmit 800 bits per second because of the larger signal bandwidth. Now, the NTSC standard television with 16,000 bits per second Do you see a trend here? Because I certainly do. And today, HD TV and stereoscopic 3D TV and even Blu-ray are only slightly above that curve that goes back to the 19th century and the sharp semaphore. So this trend is really analogous to the famous Moore's law for transistor. This begs the question, where holography is on that chart? And I have a very bad news. Because with 10 to the 16 bit per second, holography is way out there. And if I scale the graph now, holography should emerge just before the 24th century. And that's a very long time to wait for my holographic Netflix queue. Disappointing, huh? Another way to look at it, especially for you who are working with CIAN, is to compare it to the overall internet usage. And I found this very chart from Cisco, presenting the overall internet traffic in terabyte, that bit this time, per month. So a little bit of calculation and transformation. Now I scale the graph, and the holographic 3D display that we just described has the same bandwidth as the overall internet should have around 2024. Well, it's much better than the 24th century, you will argue, but think twice. This is one single display taking the overall bandwidth of the internet, the overall internet, just one display. So imagine now holographic YouTube. The bandwidth the service will require is just mind-boggling. So I was not certainly overstating when I say droning the internet in the title of this lecture. So this is the logarithmic version to show you the trend. And, but OK, I have to admit something. I exaggerate a little bit for the sake of the demonstration. And if you are actually working on computer-generated hologram, you might argue that some system already exists. And I don't want you to be mad at me, OK? Because I love holography too. And indeed, I presented here a different system. One is from Kinetic, and it's already 10 years old. It's very good, actually. The MIT Holo Video, and this one is also video rate. So it works. And another system from C-Real that support color. But on each of those systems, the image is pretty small. You can see the size in the Holo Video from the MIT. I'm not talking about 1 meter by 1 meter screen here. And also, they are missing a very important cue, is texture. And indeed, to reduce the number of pixels or the number of computation to calculate the hologram, the resolution has been downgraded. And to my knowledge, there's no computer-generated hologram, not even static one, that faithfully reproduce texture. At least I've never seen any. That is because the texture is the finest detail in an image. And it will require an exponential number of computation to display. And indeed, it will require 10 to the 16 bit per second to broadcast. So this unconditional fact broke my dream to see one day a truly holographic 3D display. And I say, Bob, unless I can improve on data communication. So bear with me here, because we are going to take a sharp turn in the presentation. And you can think about it as a digression, but remember, they are both connected. I just demonstrated that holography can submerge the internet. Now, I'm going to do the very next best thing holography can do, is to improve the internet. And this has the form of an optical switch. Around the world, data communication networks are using optical fibers. They have larger bandwidth than any other mean. And that is something that everybody here and online know. So to redirect the output of one fiber to the input of any other fiber and interconnect user, but also networks, there are switches into the infrastructure fabric. This switch function can be done with detector converting photon at one end and transmitting the signal into an electronic box, and then firing laser at the input of the correct fiber at the other end. So these switches are called OEO for optics, electronics, optics. But their response is limited by the electronic bandwidth. And we know fiber are far more better than the electronic. So these switches are a bottleneck in the data communication architecture. On the other hand, they are not bad at everything. On the other hand, they are pretty good at packet switching because they literally see all the traffic passing through them and they can analyze it. But when sheer speed is needed, nothing beats pure optical switch. And for these optical switch, there is no signal conversion, just rerouting. Here's how it works. The present technology uses micro mirror mounted on gimbal support. So the orientation of the mirror can be adjusted to reflect the light incoming from one fiber to any other fiber. It's very powerful. When the mirrors are correctly oriented, any information carried by the input fiber is transmitted to the output fiber. Whatever the wavelength, no matter the protocol, not even matter the bandwidth, the optical switch can handle it all. The problem, though, lies in the size of those mirrors. Because you see, these mirrors are about 500 micron in diameter, half a millimeter. This is quite large, actually, for MEMS. So it takes time to reorient such a mass. Moreover, the hinges are tiny in comparison, and they are so subject to failure after a certain number of movements. The time to reorient those mirrors is a few milliseconds. And this is CIAN in regard to the gigahertz of data transmission. On the other hand, you will ask, well, you can make those mirrors smaller and you solve the issue. Well, no, it's because of the power coming from the fiber. The power is concentrated on that small surface, and it starts to ablate the coating. So a smaller mirror do not stand a chance. But there exists another type of MEMS device that is much faster and more reliable than the gimbal system. And that's the Texas Instrument DMD. And DMD stands for Digital Micro Mirror Device. On such a DMD, the mirror can flip into two bistable positions. It is digital, as its name stands. And they can flip in a matter of microseconds. This is 3 orders of magnitude faster than the gimbal, which takes milliseconds to flip. So DMD are at the heart of modern projector like the one I'm using today. And they are much faster. They are also more robust because individual mirrors are much smaller, like 10 micron in size, in fact. So if I can make a switch out of those DMD, it will be a winner. The question is how to address multiple fiber with mirror that take only 2 positions. It is quite simple to address 2 fiber. Well, the mirror flip in one direction, 1 fiber, other direction, other fiber. But how to address hundreds of fiber? And this is where holography comes back again. And you can see a big smile on my face, like holography. All these pixels, they can be considered as aperture. And by carefully designing the pattern in which they are flipped in one direction or the other, you can redirect the light not by reflection, but by diffraction. So here's how it works. Imagine you want to reproduce an image like the University of Arizona A logo. You calculate by iterative Fourier transform the diffraction pattern. Then you binarize this pattern because the DMD can only support black and white image, well, at least at that speed. For the DMD, it's just a black and white image. There's no problem to display it. But for the light now, this is a diffraction pattern that will scatter the light in a very, very specific way, the way that reproduces the Arizona A logo. So the advantage are that the light is distributed over a very large number of mirrors. So the power is no more a problem for those tiny, tiny mirrors. And if you lose one mirror, you do not lose the entire image. You just change the signal-to-noise ratio. So this approach is very robust just by the fact of holography. If I have multiple sources now, like in multiple input fibers, well, you eliminate different side of the DMD. You calculate different pattern for the different side. And those patterns will scatter the light the way you want. See, for example, here I have a red and a blue laser, and I diffract half of the U, half of the A in red and blue. And I can even mix the color just by changing the pattern. So this is exactly like an add-drop multiplexer. And now if I can do that with image, optical switch is just a child play because I only need to have one single point very well located in space, the position of your output fiber. And this is what is presented on the top figure. We have 9 outputs, all addressed individually and sequentially without any problem just by changing the pattern on the DMD. And here below, you see 7 patterns on the DMD that diffract 7 input fiber coming at those different locations. So the switch is truly non-blocking, meaning you can have any configuration you want. All patterns are independent and can be changed individually. So we tested all the possible solutions here. In real life, this is how it looks like. We have 7 fiber collimated, the DMD on the forefront that load the diffraction pattern. We have a lens to focus the result into the fiber, the 7 output fiber on the background. So this is a very easy architecture. It's a very elegant setup. We even test our setup into the CIAN test bed and transmitted a video from one channel to another one without any problem with this switch, and we can change channel as we please. But we still have a tiny small issue. If not, I will be selling tons of those switches and be rich and famous, and I'm not. Not yet. See, because the mirror, they act as amplitude holograms. The efficiency is rather low, and it is predicted by the theory that the diffraction is 10% maximum, meaning we are wasting 90% of the incoming photons. This is not a good news for data communication, as you can imagine. But the theory also predicts that if we have a blaze hologram, we can have 100% diffraction efficiency, nearly no loss at all, and that will be very good indeed. The question is how to get up there. So instead of tilting the mirror, what we need is to move those mirrors up or down just by a fraction of the wavelength. And we do not need a lot of different levels. See, on that graph, it showed that with only 4 levels, I have 80% diffraction efficiency. 16 level, and I'm already at 99+% diffraction efficiency. Every photon is directed efficiently. So the problem is just that those MEMS, those piston MEMS, are not commercially available. Not because they are impossible to manufacture. Actually, it's quite feasible. But we need to invest $1 million to make the first prototype. $1 million is the price tag I was given by the MEMS foundry. And by the way, that device can also be used for other applications, like free space telecommunication between moving vehicles or ultra-fast optical tweezers. But unfortunately, so far, I've not been able to raise that $1 million. But the concept is there. We prove it works, and it can make the internet much faster. So if there is any rich entrepreneur in the audience or online, please come see me after the end of the talk, and we will have a very, very interesting discussion. So now, if the internet can be made much faster, it means I can go back to my first love, holography, 3D display. So where were we again? Oh, yeah, in the 24th century, up there. Well, we can certainly expect to improve internet by a factor of 10 or even 100 in the next decade or so. But to make holographic 3D display possible, we are talking about 8 orders of magnitude, and this is not realistic in the short term. To rephrase or to reformulate the question is, on one hand of the spectrum, we have systems such as stereoscopy that only require 2 images, but are not good at rendering all the visual cues. On the other hand, we have holography systems that require an insanely large number of pixels, but are also overkill for the human eye. We are not interferometer. We do not need sub-wavelength precision. So the question is there something in between? Something that will bridge the gap between stereoscopy and holography. Something that will reproduce all the visual cues, but on a relaxed number of pixels. And something that will save the internet from drowning under an avalanche of data. So do you remember those 3D battle maps I talked about earlier? Well, let's take a closer look at how they are made. Because if they are indeed holograms, they are holograms of a very peculiar form. They are called holographic stereogram. The name is a little bit confusing because it's close to stereoscopic, but it's what they are called stereographic, not stereoscopic. Well, they are produced by holographic printing, a pixel after another, not in a single exposure with the object on the optical table. Here's how it works. So to generate one of those maps, we start with an object that could be real or computer generated. And we render 2D perspective at different angles. We reorganize the frame, and each of those data are compressed optically by a lens onto an holographic recording medium where they are recorded as an hologram by interference with a reference beam. Those pixels generated there are called HOGL, for holographic pixel. And when we have replenished the whole surface, the entire surface of the material with those HOGL, well, we can move to reading the hologram. And we have a reading beam here that is diffracted by the HOGL into cones of light. And when your left eye might be intercepting a blue ray, your right eye might be intercepting a red light beam. So that's how you see 3D information and volumetric information in this system. It is like in each and every single little HOGLs, you have an entire image compressed. And when your eye moves, the image changes. This works with the object on the back of the display, but it also works with the object on the front of the display. The big question, though, is how many pixels do we need in a stereographic display? Because too few pixels, like 10 views per aperture, and you have the actual autostereoscopic TV that use a lens array in front of a high-resolution display. This is like integral imaging. The problem is that when you move, you see some dead zone where the perspectives are not correctly reproduced. It is inverted, actually, and this is really disturbing. And motion parallax in such a system is not continuously rendered. It jumps from one view to another. It's not a smooth transition as you expect. So on the other hand, if you put too many pixels and you try to stuff an HD TV in each of those apertures, you have about the same number of pixels as for holography when you make the calculation. This is not good either. So we need a criteria to distinguish between those cases. And that criteria is to reproduce or to approximate the wavefront curvature. This is because the wavefront curvature is what makes your eye accommodate, and that is the missing cue on the other 3D display. So we do not need the nanometer resolution like for interferometry, but just 2 rays per projected point, like this one, entering the pupil. So the calculation will show you that the actual number of pixels needed depend on the depth of field you want to reproduce. Indeed, since we are talking about angle here, to define a point in space, if it's further away from the screen, you will need more and more pixels in each of those apertures. On the other hand, a point directly on the screen will need just one single pixel, so reduction of data. Point further and further from or back to the screen need more and more subpixels in each of the aperture. So the very nice part of such a system is that it's very forgiving, and you can have system with a number of pixels that cover the entire span from stereoscopy to holography. You can adjust your number of pixels to the accessible bandwidth and address different levels of resolution or depth perception to just pick what is available. There exist different approaches to stereography. It is sometimes called super multi-view display. The system we have decided to develop here at the college is based on holographic printing, like those 3D maps, but we changed the permanent recording material for something that can record the hologram, be erased, and then refresh at will without any fatigue. This extraordinary material that we develop in-house, and it started before I arrived, I do not take all the credit, is called photorefractive polymer. And you may be familiar with permanent material like silver halide or photopolymer. But this photorefractive material is not based on chemistry, but rather on electric charge transport. And here is how it works. If you have 2 laser beams interfering, you have an interference pattern created by bright and dark fringes into the material. Into the bright region, you are generating charge pair, electron and holes. You only generate charge pair. You cannot generate just an electron alone. The very distinctive feature here is that only one of the charge species can move. In this case, I decide to move the holes. So the plus, they get trapped into the dark region of the material where they can no longer be excited by the light. That charge separation creates an internal space charge field, so electric field. And this local electric field orients liquid crystal-like molecule called chromophore that change the index of refraction of your material. That index of refraction mimic the pattern you had at the first place. And that refractive index change is your hologram. That is what is going to diffract the light. And if you want to erase that configuration, you just change it into the light beam, the charge recombine, and you start, and you can start again and again. So totally refreshable. So here's how it works. It's like exactly like for those 3D battle map, but we are replacing the permanent material with the photorefractive material. And now we can add another step, is erasing. We are eliminating the material with an homogeneous beam, and the charge we combine, we can write a new hologram. So recording, display, erase. The three basic functions of any display. Now the goal is to go faster and faster. So indeed, in our initial setup, it was taking 5 minutes to record the entire 3D image. And you can observe it for hours. In this picture, I present how we can write different holograms on the same material. And moving left and right, I took the camera and moved left and right, you can see the different side of the object. This is the motion parallax. You can also see on the last row how we can erase the hologram by just illuminating with a plain beam. After a while, after 2 minutes, the image disappears. At that time, which was in 2008, the screen was about 4 inch by 4 inch. It's about that size. Then we introduce a camera capture setup that can transmit live scene. We call it the telepresence system. It is composed of 16 cameras, each capturing a different angle. The information is then processed by a server, and a client fetches the information over the internet to print the hologram. And it's worth to note that during the data transmission, we did not overload the internet. And if you experience delay on the networks on that data, it was not because of me. I reassure you. We also demonstrate color based on RG and B and using multiplexing. Another conference call. As well as large screen, and the screen is up to 1 foot by 1 foot, that size of a very large laptop. And recently, most importantly, that all of that, we change the writing laser with a pulse laser that can record 50 holograms per pixel, 50 holographic pixel per second. Now, instead of 5 minutes per hologram, the recording takes only 30 seconds. So we are getting indeed faster. And recently we received the most prestigious recognition in science. And I mean just after the Nobel Prize. We were featured on the Disney Channel. So I will let you enjoy the movie. Just take a minute. I need to click on the image. For you people that are online, you can follow the link that is below the image. There it is. The lobby of optical science was done by Disney, not us. So they came and filmed our lab. This is our lab, very clean for once. The hologram. So they asked us to display Iron Man, what we did in color with red and yellow. The host was posing for us into the telepresence system. 16 cameras, we capture the images. You can see the images. And that's the hologram, where you can see the background and the foreground. Lloyd Lacombe, one of our professors here that works on the project.
Thank you so much to the team here for giving us a glimpse into the future. And for more awesomeness from Iron Man, make sure you check out Marvel the Avengers.
So try to beat that for outreach, because it's now on YouTube and we have thousands of hits. And I'm sure that, and I certainly hope that it inspires young people to seek a degree in optics here at the college. So, but of course, this is nice, but this is not good enough, and we very well know it. Because, quite frankly, who wants a television that produces only 2 images a minute? This is our actual refresh rate. So that is why we are working on an even faster version of the setup that will allow video rate. Video rate 30 holograms a second. That is 10,000 holographic pixels a second, each composed of millions of conventional pixels. The bandwidth is something close to 10 gigabits per second. This is large, but not insanely large. And that's our ultimate goal. A 3D display that reproduces all the visual cues. And that is what keeps me up at night, literally, is to provide you with a video rate 3D display system that faithfully render accommodation, versions, motion parallax, and texture. Well, just let's hope that it will not drone the internet on the first day we turn it on. Thank you. So if there is any question in the audience, I think we're going to start with that.